So today we're going to be speaking about some strategies in preparation of different compounds. And today we're going to speak about one strategy where we can have a nitro group with a para position substituent, or a nitro group with a meta position substituent. Now, I would even go as far as saying an amine, okay, and the COOH. Why? Because these two groups, in the first one you have two meta-directing groups, whereas in the second one you have two orthopara directing groups. So this literally makes not no sense, okay? But this literally doesn't make a lot of effort and a lot of importance when it comes to how to make them. So what you do is, you know that there's a relationship between the nitro and the amine. In fact, the nitro is the oxidized product of the amine, and the amine is the reduced product of the nitro, okay? And by knowing how to go from one to the other, okay, by going from one product to the other, you would be able to control the reactivity of the functionalities. You'd be able to control the direction of the functionalities, okay? But to do this, you need to know that to go from the nitro to the amine, you must use a reduction group, okay? A reducing agent. And this can be zinc, mercury, and HCl, so the zinc amalgam, okay? Now, this is something that you should have used for A level, but unfortunately, in this syllabus it's written wrongly, allura qatt ma toħroġ. You can use hydrogen over palladium. Normally, this would be palladium carbon, hydrogen and nickel, iron and HCl. I think for A level you might have done tin and HCl. These are all decent enough reducing agents that will be able to go from NO2 to the amine, to the NH2. I would personally prefer something like palladium carbon hydrogen, or iron HCl, or tin HCl, okay? Hydrogen nickel, whilst it will work, I'm not too keen upon, to be honest, okay? It's very similar to the palladium carbon one, but then again, palladium is better. Something like iron in HCl or tin in HCl, it's even better, okay? You don't need to add hydrogen gas, you're just picking the hydrogen in situ. To oxidize it, okay, we are using a peroxide, carboxyperoxide. Not just a carboxyperoxide, you're also adding the CF3 group, okay, which increases the reactivity. And this is something that you need to know, okay? So the oxidation is the backward reaction. It is going from NH2 to 1O2. And here we can see the reaction, okay? Here we can see the reaction, and the second one we can then see and find out how to do the reaction, okay? So for example, let's say you want to go and make 3-bromoaniline, okay? So 3-bromoaniline, all the reagents, okay? All the reagents are going to be orthopara directing. So whenever you have something like that, what happens? You'd be in a situation where, how are you gonna add 1, 3? It's impossible. So what you do is you use the nitro group. Now, the nitro group has a big disadvantage, so if you can avoid using it, please do. The nitro group is going to be, or at least will end up in a situation where you are going to have a very highly deactivated compound, okay? The nitro group will deactivate the ring. So this reaction will be low yielding and very slow. But at least it gives you the right product. Then you can reduce the nitro and get to the 3-bromoaniline. Okay? Now, okay? Now, in this case, then, you can always use this relationship between nitro and amine as part of the reaction. And remember, anytime you need to introduce a nitrogen-containing group, you do it by nitration. Okay? No matter how substituted the group is going to be, you do it by nitration. Okay? So let's say I want to make N-methyl or N-dimethyl aniline. Okay? I can do it by adding first the nitro, then reduce, then add. I would probably go for chloromethane. Oh, sorry. Apologies. I would use something like an acyl chloride. Okay? So methanol chloride, for example. Okay, not that common or familiar for you. And I can prepare the amide. Okay? And then you can reduce. Or you can use iodomethane and see if that reaction will happen. I'm not entirely sure. I believe that should work. Okay, iodomethane plus aniline. But I'm not entirely sure whether it will happen once, twice, or thrice. But that's something that you can try in the lab. Okay? In fact, that's the beauty of these things. When you are in a lab, you try the reaction and see if it happens. You know the theory. From the theory, then you go and try and do something else. Another meta-director or ortho-para-director group would be the carbonyl and the alkane. Now, here you have to be very, very cautious because reductions here are going to be very easy. Okay? Reductions here are going to be very, very easy. Here you're given hydrogen, palladium, okay, with ethanol, or normally you're more used to having the Clemmensen reduction, zinc, mercury, HCl, and heat, okay? So these will literally cleave the carbon-oxygen bond in both cases, okay? These will cleave the carbon-hydrogen bond in both cases, okay? On the other hand, if you want to oxidize, okay, if you want to oxidize, you can use chromium 6 oxide, CrO3, H2SO4, and water. Normally, there should be no reason why you want to oxidize. Normally. In fact, we will normally use the acylation to get our reagent, okay? And that's it. But it doesn't really matter, okay? So the important thing here would be that you get your product. Now, think of any alkyl substituent, and this is very, very, very important, as derived from the acyl group. Okay, so if you want to introduce an alkyl substituent, always consider what the acyl group will be. Okay, always consider what the acyl group will be. Okay, very, very important. And here we have a few examples. Okay, here we have a few examples. So if you have a carbonyl using hydrogen, palladium, and ethanol, okay, you will get the alkane. Therefore, we can use this to first introduce an acyl group, then introduce a halogen, then reduce. Okay? Or even more important, so you don't have any rearrangements, the introduction of having a butyl chain. In fact, if you were to do this reaction without without the acyl chloride, if we were to use, for example, chlorobutane, okay, you would have a rearrangement. okay, you would end up having that compound. Since the carbocation would rather form on the second carbon to be a secondary carbocation than on the primary carbon, okay, in order to get a primary carbocation. So this could really end up giving you different products, okay? This could really end up giving you a situation where unless you realize that you need to use the acyl chlorides, you will be in a position or a very tough position to get your right compounds. Friedel-Crafts conditions do not work with strongly deactivated benzenes. Okay? In fact, Friedel-Crafts reactions, especially if you're doing the alkylation, the slight activation from the methyl group will make the reactions go so and so much faster. And in fact, you will pretty much never really get, okay? You will really get only a monosubstituted product. So if you want to add a nitro group and an acyl group, first add the acyl group, then add the nitro group. Okay? First add the acyl group, then add the alkyl group, the nitro group. Okay? Now, Friedel-Crafts should be okay with slightly deactivated halobenzenes. What does that mean? If you have a chloro or bromo or an iodo, okay, even though they are slightly deactivating, they will still work. Okay, they will still work. Now, if you were to have something like a nitro and an ether group, so the ether is highly activating, the nitro is highly deactivating, so they will cancel out each other. Okay, so they will cancel out the effect of each other, which means that it's gonna be at that point either slightly weakly deactivated or slightly activated. Okay, so that is something that you would always need to pay attention for. And realize that the HFs and the alcohol here, they are gonna interact to produce H2O plus, which is a very good leaving group, and therefore it produces an electrophile. Okay, something that we've discussed during our last lesson. Now, when we're speaking about this, I will mention what we've done before, okay, and prior to this lesson, because I do believe that at the end of the day, it's gonna help you out a lot. You're gonna be in a position where you can truly improve. Do revise, I mean, Volhard, do read it, okay? At least once before your exam. I would really recommend that you have read Volhard, the chapter from Volhard, okay? At least once. I normally would recommend that you should read the chapter and write your own notes. Mela, this is something that students are afraid to do. You are normally, and this is something, an artifact of the way we teach A-level, where we will tell you, always use the least amount of steps possible. That is not true in chemistry. In chemistry, you do not care about the number of steps that you use. Okay? Tajjeb, dik hija importanti. In chemistry, you care about one thing and one thing only, yields. Will this reaction help you get a better yield? Yes or no? If yes, do it. If no, don't. And one of these reactions that can help you get a better yield is sulfonation. So, let's say you want a 1,2 compound. From what we've seen last week, the 1,2 compounds are not the preferred items because of repulsion, because of steric hindrance. Okay? So, how can you actually make sure that you get the product that you want? You block the para position. Okay? So, if you can't attack the para position, then there's no way that you can actually interact and react in the para position. And as I told you last week, sulfonation is reversible. Okay? As I told you last week, sulfonation is reversible, which means that you can first add the sulfonate. The sulfonate is a huge group. And as a huge group, it will go on the opposite, on the para position compared to your substituent. Then there's only one available position for reaction, E. Oh, sorry, ortho. Okay? And the electrophile will only end up reacting in position number 1. By removing your sulfonate, now you have managed to get your product and only your product. Now, with these reactions, you might tell me, but what about the yields? Remember, the best yield we've had last time, I think it was 36% for the 1-2 substituted product. So anything higher than 36, even 40, 45, 50, it is worth it. Okay? In industry, even adding 1% yield might mean much higher profits. Okay? Especially if it's something that is very reactive and they're making tons of it. Don't consider that in a lab, you're going to have a reaction, okay, where you are going to actually be, but where I have 1 gram or 1.1 gram, what's going to happen? Consider that in these kind of reactions, it's more of, instead of having 100 kilograms, I have 101 kilograms of a compound that might cost 1,000 euros per gram. So that would mean in the region of a few hundred thousands, if not millions. Okay, I don't feel like calculating it mentally, to be honest. Okay, so I want to do the maths. Feel free to do so. So you're making 1 more kilogram of solid that is going to be 1,000 euros per gram. So that will cost around 1,000, so 1 million euros. Okay, now these are items that you have to consider. I remember when I was doing my master's in East Anglia, I was using calixarenes. So calixarenes, if anyone doesn't know, it's literally, I was using calix 4 arenes and calix 6 arenes. Okay, so the 4 would be 4 benzyl groups attached to each other. Okay, so a benzyl is that group. Okay, so these were 4 benzyl groups attached to each other, so you can imagine. Or calix 6 arenes to the 6. And these you could buy, or you could make them yourselves. And making these was relatively cheap, easy, and therefore everyone would pretty much make them himself. Okay, so I personally would not have envisioned myself ever trying to buy these. It didn't make sense. Okay, they were so cheap. No one should have ever gone on and bought them. Okay, that's how cheap they were. So I would have always ended up, okay, I would have always ended up making them. Therefore, I never really cared about how much they cost. And I was like, this would probably cost maybe 100 euros per gram. And we decided to check how much they cost. And to my big surprise, these had cost around 1,000 euros per gram. A little bit less because they were around 750 pounds. But it was still a very big surprise. And unfortunately, I literally had to tell my supervisor, like, I'm so sorry, I didn't know. Next time I would pay a lot more attention, like I wouldn't waste so many chemicals. He was, to be honest, he was relatively nice about it, because we were only spending around 10 quid per 100 grams that we were making. But still, I was throwing away thousands of pounds because I was getting low yields. Literally, I was getting product, but I was getting low yields, okay? And then you could change the conditions to get a bit better yields, but it was going to take me, for example, instead of staying between 8 and 6 in the lab, I would have had to stay between 8 and 8. So I was happy making 100 grams per week instead of making 200 grams per week, okay? And that is something, okay, why cost is important. Now here we have an example. You can see that the R group used is quite a bulky substituent, okay? Tertiary butyl is quite a bulky substituent. And this is important because you do not want the sulfonate to attack the ortho position, okay? You want the sulfonate to attack the para position only. But once the para position is blocked, then there's only one way the reaction will go. Okay? Now, you might not have seen too much of these kind of groups, okay? Fused benzene rings. So this is naphthalene. Now, something like naphthalene, okay? Something like naphthalene is actually very important in medicine. Okay, there are quite a few drugs that would have this skeletal structure. Okay, now always pay attention where these are gonna be most reactive, both for the first substitution and for the second. In fact, now we're gonna see this. Okay, but you can always try to work it out. So as we said before, if there are two positions where you can attack, always draw both structures. Now, please remember that A, and A are all identical. Whereas B, and B are also all identical, okay? But it is something that you should always keep in mind, okay? Always keep in mind. Things could be identical. And I'm saying this because it's not the first time where I had students who told me, but what does it mean to be identical? Okay? It literally means that whatever you're doing there, it's not going to make a difference. Whatever you're doing there, okay, it's going to be exactly the same. And as we said, then we can start, and this is actually very important, we can start to try and see what happens. Attack at C1 and attack at C2. So let's say we attack at C1. At C1, you're going to have the electrophile on carbon number 2. So this would be carbon number 1, okay? Which can then go around carbon number 4, 6, and 8. Now the numbering, we're going to be doing them later on, okay? Because the numbering itself, I don't want to say it's complex numbering. It's not complex numbering, okay? It's not complex numbering, but unfortunately, and that's the real situation, the numbering here, you have to know it because it's not common. It's not the common item, okay? The number is not what we're commonly used to. So it's something that you should be familiar with, okay? On the other hand, and this is where these things become very, or at least in my opinion, very interesting. On the other hand, okay, anytime you have these structures, it's very good practice for you guys to try and draw them out. Normally I would recommend after the lesson try to draw them out. Maybe not during the lesson. During the lesson, it might be a bit tough, okay? But after the lesson, try to draw them out. Try to see what happens. And normally, you will end up being very surprised by the results. Or at least, that has been my experience until now, okay? That students would know a lot more than they actually think they do. This is a structure where even though you have a slight, okay, and I do have to say a slight mess of things, because there is, you can't say that there's not. But even though you have a situation where you have a positive charge, you spoke to the localization, there is still some delocalization in the benzene. So the first ring, it's still completely delocalized. The others, the delocalization is completely broken. Okay? The others, the delocalization is completely broken. Okay? But it is something that is, to a certain extent, acceptable. Okay? That is something that is, to a certain extent, acceptable. Okay? And you have position C2. And in position C2, you have the same structure that is going to be stabilized with the benzene. And you also have 4 other structures. But this, you have 2 structures that are going to have the full benzene ring in them. And that is going to be crucial here. Okay? In fact, the fact that you're going to have 2 structures, okay? The fact that you're going to have 2 structures, what happens? You will end up in a situation where you will get more stability. That will be the item that is going to be most stable. Okay? And therefore, that will be the item, and therefore, that will be the item that will actually take all the that will be the item that will take all of the, or most of the reactivity. Okay, so C1 is more reactive than C2. And I would always consider the positions. Now, for the second substitution, it's a different story. For the second substitution, it's a much more different story. Why? Because for the second substitution, you do need to note, and you do need to realize that there are more than 2 different positions where you can have the attack. Okay? But that is for the second substitution. But for the first substitution, there are only 2 positions. Okay? They both have 5 different resonance forms. But in C1, you have 2 resonance forms where you have an intact benzene ring. You have some delocalization, okay? Some intact delocalization on one of the benzene rings. Whereas on C2, there is only 1 position, and the other 4, you have complete disruption of the delocalization. So if you were to add the nitro group, then you will end up in a situation where you will have 84% on C1, 8% on C2, and the other 8% would be other reagent, other compounds. So disubstitution, maybe some trisubstitution, okay? Maybe some compound that didn't react. But they do not have to add. So this is something very important. Whenever you have a reaction, you do not need, and this is, let me make this clear, you do not need to get in a situation where everything must be exactly as you think. Okay? that is normally, in fact, not the case. That is normally something that is completely not the case, okay? Normally, you do end up with less than 100%. And it makes sense, to be honest, to have less than 100%. Why? Because at that point, okay, at that point, that 100%, what does it mean? That 100% would mean that all the products they're accounted for. And you do not normally account for all the products. Okay? Now, so then, if you have an activated, if you have a substituted naphthalene, what happens? Okay? If you have a substituted naphthalene, something again must happen, because these items are going to be okay, quite good when it comes to reactivity. So what will actually happen, and what do we do? So my idea has always been this one. Whenever you have a situation where, okay, whenever you have a situation where you need to try different things out, okay, actually try and see and add the structure. I don't think they have the resonance forms here. We'll be doing the resonance forms again in a different chapter, okay? But don't be afraid to try them. Don't be afraid to say, this is going to be that chapter, this is going to be this chapter, this is going to be doing this is going to be doing that, okay? Truly do not be afraid. Why am I saying this? Because I've had students who told me, but sir, these are not what I'm familiar with. These I have never seen before. Try them. Even when you are studying, try them. You'd be surprised how much you remember. You'd be surprised how much you know. Okay? Always try. These things you should always try. Okay? Something that I cannot emphasize enough. Okay? Always try. And the more you try, the better you will do. And the more you try, the easier things will get. Okay? I'm telling you this because it becomes exceptionally important. Okay? In your mind, you might be like, this is all crap. I'm pretty sure no one will tell me I don't know what I'm saying, but for you it might be that what's the problem? Okay? But the reality is that at the end of the day, these are all items that you should know. Okay? These are all items that you should be able to do. For naphthalene, okay, you will have a similar situation with the ortho and para. But remember, at this point now, it's not just ortho and para. Then you would have a situation, or you would have a position where you will also have other items. Okay? You would also have other items. So you would need to keep those in mind. The other items would be that ortho, but what about these ones here? Are these ortho or para? And you would need to see how to calculate them. Again, we're going to be doing this, okay, from a slightly different perspective as well. And we're going to try and do this and see what happens. But I'm just telling you, just pay attention so that we would be in a position where you can actually get these right and you can actually get these correct first time round, first time of asking. Okay, for now, don't worry too much about it. Okay, for now, don't worry too much about it. The activators, like a NO2, okay, the activators normally, they push the electrophile away. Okay, so the activator normally would assume to be there, but they will push it away. They will push it to position number 5 or 8. Okay, and the difference between 5 and 8 is actually because of the difference will be simply as a product of the repulsion. Okay, so the repulsion there is going to be a big item. Okay, it will be a big part. So that is something that you would also need to know. But again, I wouldn't worry too much about this, because at the end of the day, the important step isn't truly what's happening, but rather why. Okay, and the why is something that you would be able to do with ease over and over and over again. Okay, but that's something we're going to be discussing later on. But keep it in mind, because even though we're going to be discussing it, it's not going to be a situation where it's going to be something that's going to be as the forefront of whatever we're going to be saying forever. Okay, so I'm repeating it, but at the same time, keep in mind that it's something that is not going to be the most important, the biggest deal for us. Now, for today, I have finished benzene pretty much and aromaticity. Any questions? Any questions? Okay, so let's stop the recording.